So this is a presentation on the absolute value and some of its properties and proofs of those properties. So the absolute value of a is equal to negative a when a is less than 0, and a when a is greater than or equal to 0. So this is a graph of what it looks like. You can see that 1 is mapped to 1, 2 is mapped to 2, 3 is mapped to 3, negative 1 is mapped to 1, negative 2 is mapped to 2, negative 3 is mapped to 3. Get that V shape. So the first property we're going to prove is that the absolute value of a is always greater than or equal to 0. So we have to look at this, we have to look at the two cases, when a is less than 0 and when a is greater than or equal to 0. When a is less than 0, then negative a must be greater than 0. And so the absolute value of a, which is equal to negative a in the case where a is less than 0, must be greater than 0. And in the second case, when a is greater than or equal to 0, the absolute value of a has to be equal to a, which is greater than or equal to 0. So we've proved it for both cases. When a is less than 0, the absolute value of a is greater than 0. And when a is greater than or equal to 0, the absolute value of a is greater than or equal to 0. So now we're going to prove that the absolute value of a being 0 implies that a is equal to 0. So let's start with the first case. So if a is less than 0, then negative a is greater than 0. And the absolute value of a is equal to negative a, which we just said is greater than 0. So then a cannot be less than 0 because we've run into a contradiction. A being less than 0 implies that the absolute value of a is greater than 0, but we know the absolute value of a is equal to 0. That's our starting assumption. So we've run into a contradiction. And testing the next case, a is greater than 0. That means the absolute value of a is equal to a, which is greater than 0. And so, again, we've run into a contradiction because the absolute value of a needs to be 0. So a cannot be greater than 0. So that leaves only one option, that a is 0. And going in the reverse direction is very easy. It's just by definition, the absolute value of 0 is 0. The next property we're going to prove is that the absolute value of a is greater than or equal to a. So when a is less than 0, then negative a is greater than 0. And so we've got negative a is greater than 0, which is in turn greater than a. If a is less than 0, then 0 is greater than a. So negative a is greater than a by transitivity. So the absolute value of a is equal to negative a, which is greater than a. And in the second case, when a is greater than or equal to 0, well then the absolute value of a is just equal to a. So when a is less than 0, the absolute value of a is greater than a, and when a is greater than or equal to 0, the absolute value of a is equal to a. So this is true for all a. The next property that we're going to prove is the absolute value of a squared is equal to a squared. So if a is less than 0, then the absolute value of a is equal to negative a. So then the absolute value of a squared is equal to negative a squared, which is just a squared. And the next case, a is greater than or equal to 0. That means the absolute value of a is equal to a. And the absolute value of a squared is equal to a squared. So for both cases, we see that the absolute value of a squared is equal to a squared. So this next property is just a simple consequence of the last one we just went over. If the absolute value of a squared is equal to a squared, then the absolute value of a has to be equal to the square root of a squared. You just take the square root of both sides. So now we're going to prove that the absolute value of a times b is equal to the absolute value of a times the absolute value of b. The absolute value of a times b can be rewritten as the square root of ab squared, which is equal to the square root of a squared b squared. You can distribute the square, and then we can distribute the square root to get the square root of a squared times the square root of b squared. And then, again, that can be rewritten as the absolute value of a times the absolute value of b. This next one, the absolute value of negative a is equal to the absolute value of a. This can be proved easily using what we just proved. the absolute value of negative a is equal to the absolute value of negative 1 times a, which, by what we just proved, is equal to the absolute value of negative 1 times the absolute value of a, which is equal to 1 times the absolute value of a, which is just the absolute value of a. So the next property is that the absolute value of a minus b is equal to the absolute value of b minus a. The absolute value of a minus b can be rewritten as the absolute value of negative b minus a, and then by the property we just proved, that is equal to b minus a. One's pretty easy. The next property that we're going to prove is that the absolute value of a plus b is less than or equal to the absolute value of a plus the absolute value of b. The absolute value of a plus b can be rewritten as the square root of a plus b squared, and then we can expand that out to a squared plus 2ab plus b squared, and then we can rewrite a squared as the absolute value of a squared, rewrite b squared as the absolute value of b squared. And then this next step, what we're doing here is we're replacing a with the absolute value of a and b with the absolute value of b. If you remember one of the first properties we proved, the absolute value of a is always greater than or equal to a. Said another way, a is always less than or equal to the absolute value of a. So a will always be less than or equal to the absolute value of a, and b will always be less than or equal to the absolute value of b. So the term 2ab will always be less than or equal to the term 2 times the absolute value of a times the absolute value of b. And if that's true, then since this term is the only thing that's different between these two expressions, then this expression will always be less than or equal to this expression. And so the square root of this expression will always be less than or equal to the square root of this expression. And then we can just, this is the same form as the first expansion over here, so we can just revert that or factor it back into the absolute value of a plus the absolute value of b squared. And then the square root and the square cancel out to give us the absolute value of a plus the absolute value of b. So the absolute value of a plus b is less than or equal to the absolute value of a plus the absolute value of b. Now we're going to prove that the absolute value of a minus b is greater than or equal to the absolute value of a minus the absolute value of b. The absolute value of a is equal to the absolute value of a minus b plus b, which we know by the last property is less than or equal to the absolute value of a minus b plus the absolute value of b. And then we just need to subtract the absolute value of b from both sides to get the absolute value of a minus the absolute value of b is less than or equal to the absolute value of a minus b. And another way of writing that is just the absolute value of a minus b is greater than or equal to the absolute value of a minus the absolute value of b. Now we're going to talk about what it means for the absolute value of x minus a to be less than epsilon. You see this a lot in calculus. So what does this mean? Well, intuitively what it means is that the distance between x and a is less than epsilon. So you can think about a being a point and then epsilon being a radius around that point. And so if x satisfies this inequality, x is within that radius. So we can expand it out and see what it looks like. The absolute value, let's look at the case where x minus a is less than 0. So when x minus a is less than 0, then the absolute value of x minus a is equal to negative x minus a. And so we've got negative x minus a is less than epsilon. And then multiplying both sides by negative 1, you get x minus a is greater than negative epsilon. And then adding a to both sides, we see that x is greater than a minus epsilon. So when x minus a is less than 0, then x is greater than a minus epsilon. This makes sense because for x minus a to be less than 0, then x must be less than a. So x is less than a, so it falls on the left of a. It still must be greater than a minus epsilon, because a minus epsilon is the lower bound there. And in the second case, we see that x minus a, if that's greater than 0, then the absolute value of x minus a is equal to x minus a. And so we have x minus a is less than epsilon, and then adding a to both sides, we see x is less than a plus epsilon. This makes sense because x minus a being greater than 0 implies that x is greater than a. So x is to the right of a. And so x is to the right of a, it must also be to the left of a plus epsilon, because that's the radius, that's the upper bound. And so putting those two inequalities together, we can see that a minus epsilon is less than x, which is in turn less than a plus epsilon. And we can see a picture of that here. Here's our point A, and a distance of epsilon to the left, we have a minus epsilon, and a distance of epsilon to the right, we have a plus epsilon. And if x satisfies this inequality, then x is somewhere within this interval. So here's the interval, a minus epsilon, comma, a plus epsilon. X is within this interval if it satisfies this inequality. That's what the inequality means. The last, or one of the last properties we're going to prove is that the absolute value of a minus b is greater than or equal to the absolute value of a minus the absolute value of b. This looks exactly like the one we proved back here, except there's an extra set of absolute value bars around the right side. So how do we get this? Well, we start with the absolute value of a minus b. We know already that that's equal to the absolute value of b minus a. And we know that that's got to be greater than or equal to the absolute value of b minus the absolute value of a, which we know we can rewrite as negative absolute value of a minus the absolute value of b. And now if we multiply both sides by -1, we see that negative absolute value of a minus b must be less than or equal to the absolute value of a minus the absolute value of b. The direction flipped because we multiply both sides by -1. And so now we have this inequality here, and if we combine this inequality with this inequality right here, we combine the two together, you see we have negative absolute value of a minus b is less than or equal to the absolute value of a minus the absolute value of b, which is less than or equal to the absolute value of a minus b. And you note that this looks very similar to this here, and it's really exactly the same. And so we can rewrite that in a more simple way as the absolute value of x minus a is less than epsilon. So doing that same thing, we rewrite this as the absolute value of what's in the middle here, which is the absolute value of a minus the absolute value of b, is less than or equal to the absolute value of a minus b, which is the positive side. And of course that's the same as just writing it as the absolute value of a minus b is greater than or equal to the absolute value of a minus the absolute value of b. The last property we're going to prove is that the absolute value of the absolute value of the absolute value of a is equal to the absolute value of a. So this is really simple. We know that the absolute value of a is always greater than or equal to 0. So that means that the absolute value of a has to be the absolute value of a. Because if the input to the absolute value is greater than or equal to 0, the output is just the input. So, and here's just a summary of everything that we've covered. All of the properties that we've derived, the definition of the absolute value, its graph, and the meaning of the absolute value of x minus a is less than epsilon.